Excited to basically look at every single technology that I try not to make my title too long, but we will at least touch on some of these, which is fantastic. So just to recap the title of this talk, it's titled Using Django, Docker, and Scikit-learn to Bootstrap Your Machine Learning Project. Something I do want to point out is that all these slides are actually available with a bit.ly link on the bottom left-hand corner. I also will be sharing on Twitter, and I will also be sharing the code, which I will not be doing any live code today, but I do have a repository up and would love people to use things, break things, tell me that I need to add things, so that'd be really fantastic. But yeah, so I would like to start off a little bit with a story about something that happened to me recently. So I'm guessing many of us use some kind of communication tool like Slack at work. Yes? Okay, great. So on August 1st, I got this fantastic ping from a coworker of mine, Matthew, who basically was like, hey, I've got questions. The interface on this model changed. What happened? What's going on? Blah, blah, blah. And I'm like, wait, hold up. There's a few models, and there's a lot. What changed? What explicitly is the model version you're talking about? I don't understand. And I think this right now speaks to kind of the problem space I'm currently in, which is tooling around data science teams. So yeah, this just happened to me on August 1st, and it's only August 15th, so the struggle is real. I'm still in this problem space trying to think through this quite a lot, and would love to hear any feedback you have. So August 1st, Matthew pings me, and I'm like, okay, well maybe I can go and piece together what this model is. I go jump on GitHub and look at where the data scientists are chucking code in. I go into one of the data scientists' projects repository, and there's just 10 Jupyter notebooks in there with a lot of code, a lot of things I don't understand in them, and I'm just like, okay, I have no idea which of these Jupyter notebooks dumped the model that is on this Kubernetes service that Matthew, you were using. So hold on, let me go look. So I go look and see if I can piece together the story from the pickled version of the model. And we store those on S3. And looking at S3, you'll notice June 12th, July 25th. OK, there's something called latest, which is maybe correct, I hope. But you'll notice the size of the model is exactly the same. And there's been 5 to 6 weeks between these two models being dumped in there. And I'm not exactly sure which one it is. So that is pretty much my struggle every day. I'm kind of somewhere in this place where I'm lost. I'm not exactly sure which model someone's using. Yes, this is the correct version. Yes, this is the interface. Where are we with our data science team, and what are our best practices? So I'm going to talk a little bit about a few things today. But before I get started, I did want to do a quick introduction to who I am. Hi, my name's Lorena Mesa, and as our session runner indicated, I am totally a big Star Trek nerd. I paid way too much money to meet Captain Jean-Luc Picard, which was fantastic. But something a little bit about me is I've actually come out of the world of being a political scientist. So a few years ago, I was like, I can do SQL and Python, and I like this code thing. So I went through an immersion program at Dev Bootcamp in Chicago, and I've been with the Sprout social engineering team ever since May 5th, 2014. It's been really exciting. In my time there, I've been on the platform team, working on 2 different parts of the platform. And last year, and some change, I've been on our brand new data science team. I will talk a little bit about the anatomy of our data science team, but what I do want to point out is our data science team is newer, and we are growing quickly, which is kind of where this talk comes from. Some other things I do, I help run PyLady Chicago, and I do sit on the Python Software Foundation Board of Directors. I think there's a few of us here at DjangoCon, so if you do have any questions or want to know more about the PSF, this is just my call to you. Come speak with us. We're super happy to get to know who you are and learn more about your needs. So in regards to today's talk, we're going to be kind of going through these 5 items. We're going to chat a little bit to get some common language around what machine learning is. We're going to talk about the anatomy of a data science team, because I know with Django and with Python, we can get people from a broad variety of disciplines. So I do want to make sure we talk a little bit about data science and how my team kind of functions. Then we will high-level talk about the engineering of a machine learning problem. We'll then move into thinking about machine learning engineering using some of the latest and greatest buzzwords like Docker, Django, because we're at DjangoCon, Scikit Learn, and some other goodies. And then we'll kind of leave with some open questions about what could be next for the project I'm working on. Maybe what are some ideas for you all if you work on data science teams, what we could use in the ecosystem for data science infrastructure, and then also tools for more learning. So great, what is machine learning? I always get a little bit of a kick out of when people think about what machine learning is, like input. Hi, I'm Johnny 5. If you don't know what Johnny 5 is, it's a really ridiculous movie, kids movie from when I was little, where you have like a super fancy, like intelligent robot who can do all the things. And I think sometimes that's what people may think when they think of machine learning, especially if they don't work in an organization that has some kind of data science practice already. But for lack of a better word, I do like to always try to find some common jargon just to kind of orient myself and think through, well, when we talk about machine learning, what is it that we're actually getting into? So rather than read this wall of text, I just want to kind of highlight some of the big things here. So machine learning, it's a subfield in computer science, does pattern recognition, computational learning, artificial intelligence, blah, blah. I'm sure we've heard a lot of that. So I don't really care so much about that. What I do really want to focus on is machine learning explores the construction and study of algorithms that can learn from and make predictions on data. So the big thing here, algorithms. We all know what that is. Data, we work with it all the time, and making predictions on data. Cool, we now have some grounded language to think about machine learning. But let's not stop there. Let's think about it maybe in a little bit more of a traditional way that some of us who maybe have computer science degrees may have been exposed to machine learning in a language like this. So I found this language to be very useful. It comes from Tom Mitchell, computer science professor at Carnegie Mellon, where he frames machine learning with these three pieces. The emphasis here is that a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T, as measured by P, improves with experience E. So when we are talking about our algorithms are going to be doing some task. They're going to be using data, and from that data, we're going to be trying to derive some insights so that we can go ahead and make predictions on what new things may be happening out there. Depending on the features you're building, there's going to be some task, some kind of thing we want to accomplish. And how do we know if we're doing things correct? Well, we have some idea of a performance metric. Okay, so just because I like to kill everything with details, I think it's always good to have a little bit of a toy problem to think about when we think about what might be some ways in which we do machine learning in our day-to-day, and what are some toy projects we work on. So Sprout Social, where I work, is a largely business-to-business social media management and analytics tool. So something we work a lot with, social media data, so text data. That's a really big thing for me. So text data, that's something that I think we might have all heard about. We've all had things like the spam filter in our inbox. It marks something if it's spam or not. Well, let's maybe take that example a little bit further and think about a different example. So the idea here of something else we could think about as a machine learning problem could be predicting altruism with a naive Bayes classifier. So I'm guessing some of us, I hope many of us, like pizza. Yes, especially if it has like the words free associated with it. That makes me really excited. So what would you all do to get free pizza? Do not scream it out loud. I'm just going to brainstorm up here. Let's see, would you maybe run a marathon? Perhaps, because maybe those carbs are so much better after you run a marathon. Would you, I don't know, would you do interpretive dance in front of DjangoCon for 45 minutes? Maybe. I don't know what your requirements are for getting free pizza. But this is actually a really fun little toy example that someone actually put into the world and actually clean data for us so that we can actually start working on thinking about measuring and predicting altruism with this idea that if you get pizza, someone gifts you pizza, that's an altruistic act. So where does this example come from? On Reddit, there's a subreddit called Random Acts of Pizza. And essentially what this subreddit is it's basically invites people to come on and say, hey, you can make a request. As you'll notice here, there is some structure for how our request happens, which is pretty nice because in the era of unstructured data, having some structure to your data is great, especially when you're doing machine learning. So in line item 2, we have write your request, post, and submit it. Remember to start the title with request. So yeah, there's some ideas here, but essentially this is a subreddit on Reddit where people can go and basically make requests for free pizza, and then the community will upvote or downvote. And based on the rules of how this works, eventually when you have so many votes, yep, you're gonna get a free pizza, or someone might just buy it for you. So if you're hungry tonight, maybe you can do this tonight. Some examples of text of free pizza. Oh goodness, I really got a kick out of these. The first one, I actually have money for the pizza, but all I have is a $50 bill. And the delivery boys don't accept anything larger than a $20 bill. So that was actually the text of someone's request. Another request that someone made was, I've got a guitar in one hand and on the other a pizza pie. So I guess they were just like trying to get someone excited. They're like, I'm already almost there. You just have to buy me the pizza. But as you can see, these kind of requests, they can be all over the place. They can be kind of silly, and some of them are actually a little heartbreaking to read. So in this toy example, the data science competition website Kaggle actually already had cleaned this data set and made it easily downloadable. So it's probably very hard to see, but on the right-hand side is a snippet of some of the JSON blobs that represent the training data for this problem. You've got a lot of features in there, including the request text, which is some examples of things I gave you. You've got the number of votes. You have the user information of who requested it, the date it was requested, things like that. So that's kind of example of your training data. And then essentially what this problem does is it says, hey, I want you, given these 5,671 requests, of which 994 of them are labeled as true, and the rest are labeled as false, I want you to write a model, a machine learning model, that can actually predict and tell me if, when I get a new request coming in, if that request is going to be successful or not. So for a machine learning problem, this might be an example of a classifier. I don't know, maybe you've got a new wonky app idea where you want to, I don't know, hack your way to all the free food in the world. Maybe this is your way of like bringing machine learning to your application. So you have some idea of text data, and you've got some historically labeled examples of things that were successful or not, and then you can use that when you're constructing your model to help you make future predictions. So to reframe this in the language that we saw earlier from Tom Mitchell, we have the task, which is classifying a piece of data. Essentially, the question is a pizza request successful? Or if we ask it differently, is this an act of altruism or not? Our experience here is going to be the label training data, which essentially is like a CSV where you have a request ID, and you just got a Boolean representing true or false if that request was successful or not. And our performance measurement, is the label correct? That's pretty much your performance measurement, because when you're working with labeled data and you're actually going to go ahead and predict on some of that training data, if you have the label already, you can go just and check and see, hey, did I actually successfully predict this thing or not? So in the example kind of machine learning, maybe you have some kind of classifier problem like this. You have your task, you have your experience, and now you've got some notion of a performance measurement. What next? Okay, so we've talked a little bit about what machine learning may look like for you as an engineer, what kind of decisions you have to think about, what kind of data you may be working with. So it could be text data, it could be other things about the pizza request. Maybe you're looking for if something is incorrectly capitalized in the request. Maybe there's other characteristics of the data that you want to look at beyond just like the words that are in it. Well, with a data science team, something to think about is that you've got kind of a few folks who are working on these problems. It's not just going to be not just your developers. So kind of borrowing this from IBM's UX personas as applied to engineering, they highlight the idea and the differences between the app developer, the data scientist, and the data engineer. So the data scientist is actually going to be someone who's going to be going in there doing a lot of the feature engineering. They're the ones who are going to be trained on the different statistical methods and algorithms. And your data engineer is going to be the one probably building the pipeline, the infrastructure around this, making this thing happen. And then your app developers perhaps are the ones actually bringing the model and putting it into the application and making it so a user can actually use this feature or not. So in that world, let's talk a little bit about my data science team. So you may have seen this Venn diagram of madness, as I like to call it before, where, with the idea that someone has all of these skill sets, to me, is just a total fallacy. The idea that you're going to have math, stats, subject area expertise, and computer science, and that's the unicorn, which allegedly is a data scientist. No, I can tell you that's definitely not the case. In the kind of the context of my team, we've got a team that's been growing pretty quickly, like I said, about a year and some change. So we've got 4 data scientists. We've got someone who comes from natural language processing, a PhD, who has spent a lot of time in computer science and working with NLP. We have folks who've come from predictive analytics, economics. Now we also have a person who came out of their postdoc doing chemistry. Then there is me, the lone sole software engineer in the team. And like I said, I came from the platform engineering side of things. And I've done a little data analytics in my time as a person in the professional world. We do also have some designated infrastructure support, but largely that is still kind of in our wheelhouse. So why is that a problem? Great, we've got PhDs who are wearing the title of data scientist. There's me, and we have some infrastructure report. Why do I care about that? Well, I think this can give you an idea. So from the keynote that Jack van der Plas did this year in Portland, he talks a lot about the variety of tools that are in Python's scientific stack. You've got scikit-learn, you've got a lot of different IDEs you can use, like DataGrip. You have tools like pandas. You have a lot of visualization tools and plotting tools, and also just like the actual work of developing the model and executing. You've got things like Jupyter Notebooks. This is a big world that people can pick up and select tools from. So that's cool. Why is Python the place that people are going to if they're doing a lot of modeling work? The good thing I like to think about, and why I get excited about data science in Python, is namely that it really is a place where we can kind of mash a lot of things together. In the scientific community, there's a lot of work, for example, in the astronomy field, using Python to do a lot of analytics and visualization. Kind of, again, reframing what Jack van der Plas highlights, Python acts as a glue. It plays well with other languages. We've got our batteries included kind of idea here. We don't have to go and write a lot of proprietary code just to go in and start working with data right from the get-go. Python's simple and dynamic, and it has an open ethos well-suited to science. So that's all fine and dandy, but again, on my side, I'm the one software engineer on my team with people who come from a variety of different academic disciplines, and the kind of tools that they can use can broadly vary depending on the types of machine learning problems we're working on. So to kind of think about what is the motto for my team, or maybe what's the motto for me as a person supporting a data science team, I'm going to modify Professor Ralph Johnson's quote here. And instead of saying before software can be usable, it must be reusable. I'm going to say explicitly before machine learning can be usable, it must be reusable. We have a lot of different expertise. We have a lot of open source tools. We have a lot of different kinds of problems people can use. And I think it's leading to, it can be a little overwhelming, is kind of the thing I want to highlight. So back to this idea of machine learning. One thing that we've had to think a bit about is what kind of problems are we going to answer, and what does that look like when we're answering those problems? So back to that example of the predicting if you're going to get a free pizza or not. So we might have text data there, but that could, depending on the machine learning problem you're working on, you might have a variety of other data sources that you're integrating. And this kind of component of like shaping the data in the format that you need, selecting and then maybe munging the data into the format that you need as well, can be quite expensive. So we call this feature engineering. This representation kind of on the left-hand side gives kind of a broadly simplistic idea of what may be a pipeline for a supervised learning approach to machine learning. So you can see like maybe we've got data in our in our production databases, maybe we have logs, maybe we have, so examples of some of the logs, maybe we have some metrics in which we're kind of capturing how people are using the application. Maybe we've also got some proprietary data sets that we've paid for. There can be quite a few series of things that we're taking together and we're integrating and we're globbing together into a new format. So this idea here of getting the data, merging it together, and then that feature extraction and pre-processing, that is going to be a lot of the work of our data science team. Then we have once we have data in the format and we've selected the features that we want, we can then go ahead and apply our learning algorithm. Great. From there, we're able to get a model, and then using that model, we can go and make predictions. In the example of our classifier, we can go and make predictions on future pieces of data and say, hey, that thing is successful, or hey, no, it isn't. But the broad idea here is we're munging a lot of things together. There's going to be different areas of expertise, and depending on who is doing what work, we need to think a little bit more critically about that. And so this gets me to one really big question. The way that application developers use the data that we're collecting and our proprietary data versus how I might be using the data versus maybe how data scientists perhaps themselves are even using the data can be quite different. And we've actually got an entirely different kind of infrastructure that we need to start developing and building. And with that, the question then ultimately becomes, where is the handoff between data science and production? What does that look like? What should our social contract be? Because the way that I'm collecting and shaping data and the kind of data pipelines that we're laying down aren't going to be of importance to the application developers who are responding to user-facing features. So let's break this down a little bit. Okay, so in the kind of flows that I'm going to be talking about, we've talked a little bit about the get and shape the data. That's the first thing. The second step of that is training the model on the data. Third, we want to pickle the model. We could save it with something like, in Python, joblib. And then fourth, we can go ahead and use it and make predictions on the data. So in this kind of example here, using Python's ecosystem, you might have some kind of script, and this is quite simplified, but you might have a script like what we see in the left-hand side. So in the Python scientific stack, we have sklearn. Why sklearn? Why not TensorFlow? sklearn is tried, true, and blue, and that's actually what my team uses. So you might have something like this, where you're saying, okay, we've got the example of the pizza. We have data that we've been collecting, and now we want to be able to apply a model and make predictions on it. So using scikit-learn, we actually have all those algorithms built in. So naive Bayes, one variant of that is the multinomial naive Bayes, and the flow is going to kind of look like this in the Python code you may receive. Something to the extent of, hey, let's split that data into the training and the training set and then the test set, and we're going to go ahead and fit that multinomial model or whatever model you're using. You're going to fit it on that training data. And essentially what that does on the training data is it starts to represent whatever features you selected. So if you're doing something like working with words, perhaps you're turning that into a numerical vector saying, hey, words that appear most often in requests that are successful for winning a pizza, here's their kind of histogram count. And the ones that aren't successful in getting pizza, here's a vectorized format of those word counts. That could be one example of a feature. There might be other features you're including, and you can represent that in a numeric format. But essentially, when we're fitting against historical data, there's a process like that happening underneath. Once you've fitted on that historical data, you can go ahead and say, hey, I've now got a model that's ready to go ahead and be used. And that's where we're going to go ahead and dump out the model in a pickled format. So again, that kind of shaping of the data, like what kind of prep work am I going to be doing? I'm not doing a talk that's very deep on Scikit pipelines. If you are curious about that, there's a fantastic talk I recommend from PyData Chicago, August 2016, about 40 minutes that goes in and talks about different transformations you can use and things like that. I have it linked to my slides. But that all being said, when you have your data, you're going to have to do some kind of munging of it together, getting it to work, and you can use transformers from scikit-learn to actually get it in the way you want. So to think back to the idea of what might be an example of a transformation. Perhaps you have a bag of words with a lot of a, the, but. We call these stop words. These are words that don't provide a lot of context, perhaps. Maybe the frequency of these words can throw off or introduce bias into your model that says, hey, I'm going to over-bias and overestimate that this is likely going to be a successful request or not. So a transformer might be breaking your bag into a bag of words, removing stop words. You might also be doing something like stemming, which is treating words like shop and shopping as the same word. You're going to remove that ing. But transformers like that, and you can write your own custom ones. You can do that with the scikit-learn pipeline operators. So when we're back into this flow, we've got training examples. We've got the forming of the data in the format it needs, and then we're going to go ahead and apply that learning algorithm. What's pretty nifty too about scikit-learn is you've got a variety of things in there. So if you are kind of new to machine learning, there's a lot of ease of use for you to go ahead and start getting to work pretty quickly. So I would encourage you to go ahead and explore a lot of that. And then you do have some metrics that are also built into scikit-learn. We'll see that a little bit at the end. But for the context of the machine learning that I'm talking about and that I work with, this is historically our flow. We've got supervised learning. We have some previous data that's been formatted in some way. We'll use scikit-learn, apply transformations, get it into the format that we need. Then we can go ahead and fit the model on it. We'll take that model from scikit-learn, and then we can dump that model using joblib in a pickled format, and then that thing is ready to go. Cool. Okay, so I was talking a little bit earlier about reusability. So we've got a flow. We've talked a little bit about what the code may look like for if you're using Python to do machine learning, explicitly following with the example of a supervised naive Bayes example. So reproducibility does matter. So how do we engineer for that? Okay, I really think social media data is just so fantastic. Imagine you have to develop a machine learning model that says, hey, the sentiment of this tweet is positive, or it's like a warm, good feeling. You know, however you want to slice and dice it, you have to like separate negative from positive. Well, here's the thing. Emojis are a part of text data. The idea of having, I think it's called tears of joy, people use that so differently. You have some folks who think that that's actually like someone who's like sneezing and crying. You have people who use that and they may think that it's like a very positive, exciting thing. So the example here from the tweet, it says, I'm laughing so hard, tears of joy, tears of joy, tears of joy, lots more tears of joys, hashtag mentally dating Justin Bieber. And the shirt says single taken X mentally dating Justin Bieber. So if I were to ask you, is this a positive or negative thing? I'm very curious what you would say, because I would say, not so positive. I'm not a huge Justin Bieber fan. Like, I would think that tears of joy is tears of just like utter destruction. I don't care. This is not a positive tweet. Another really fun one that I've come across before is the purple heart emoji. So, you know, super sad that Prince is no longer with us, but Prince, purple is the color of Prince. And if you're looking at tweets that use the purple heart, especially around the anniversary of Prince's passing, which I believe was April of this year, was the 1-year anniversary, you start getting a lot of purple hearts. And so let's look at this tweet. The Prince estate has announced at Pantone's new purple hue, named in honor of Prince's famous love symbol. So to me, I'd be like, oh, that's so cool. We're remembering Prince and we're empowering Prince. To other people, they might still just be, you know, watching Purple Rain and just utterly destroyed by things. So, you know, we have all these examples of kind of inconsistencies, right? So reproducibility does matter. If I have a machine learning model that's predicting the sentiment of something, ideally we would want it to be consistent, right? Yeah, I would hope so. But there's a lot of context there. And so this is where things can get a little tricky. And I'm not even going to start on the hashtag LOL sob, because that's a silly one. So the idea here about data and kind of data governance, who owns the data, who's doing what, how are we going to get consistent results? So in the pipeline operator of things, I want to be able to look at my system and think of black boxes. I know that I've got the black box that shapes data and does things. I've got the black box that spits out a model. And then I've got the black box that can go ahead and be called and make a prediction, right? So I'm going to say as an engineer, what I care about is developing tools that will help me get this reproducibility. So that's where I'm going to start saying Docker is fantastic. And also, I just really like Docker's imagery. It makes me very excited. So containers. There is a very awesome talk later today on Kubernetes. And there's also a talk saying, like, I think the talk is end-to-end Django on Kubernetes, which is fantastic. But yeah, so containers. Let's get into containers and talk a little bit about it. So Docker. I'm guessing probably most of you have used it, but it's always good to get a refresher if you have not. So you can think of Docker as basically a big executable tarball that has an explicit format. So for me as an engineer, I might be like, oh, the code that actually does the thing, any kind of libraries I need to help me write the code to do the thing, and maybe any system tools I need. Cool. Well, here's a fun gotcha. In data science, that might also include this data, because we don't want this weird inconsistency around the purple heart, the LOL sob, whatever is the latest and greatest thing that someone's introducing into the world. So yeah, data is also probably going to be a big thing if you're talking about supervised learning problems. So Docker can also, when we think of Docker, maybe that tarball can also learn how to get that training data down so that when we introduce new versions of models, it can retrain on the same thing, because consistency is good. And again, why use Docker? I just have to steal from Kelsey Hightower, who eloquently said, the first rule of Python is that you don't use the system installed version of Python. I'm sure many of us have struggled. I know, having run Django girls quite a few times, telling everyone, do not use the Python that's installed on your machine. I will LOL sob all day. So obviously, as we know, setting projects up can be difficult, but then introduce other complications with machine learning, like the data that we're using, the correct order of transformations that we have to do. There's other things that start to become more complicated when we talk about machine learning problems. So for the Docker end of this, I'm going to say what's really cool is Docker allows us to make a container, which basically takes a snapshot of how that code works at that given moment, and then we can just put it somewhere. And then we could check it out later if we want. So we do this with a Docker file. And essentially what the Docker file does is you'll have steps in your code. And what's really nifty is if you have the same procedure in your Docker file time after time, you won't need to re-download everything. It's essentially caching layers. So only when you make changes in your Docker file will it have to go and re-download things, which is great. We're now making our lives a little bit easier with setup. So when we write the Docker file, then the second step is you build the Docker image, which would look something like Docker build with the tag. This is the name of the model, predicting altruism. Give it a tag of latest. And then if I wanted to run that Docker container, it might look like from the command line, Docker run detached, mirroring, associating port 8888 to 8888, and use a mountable data directory volume. So as an example of a Docker file, essentially what this is doing top to bottom, this is an example of maybe what I would give a data scientist for them to go ahead and start working on their stuff so that I can say, okay, now save things so that I can check things out when you give me the thumbs up that you've got a model that you want me to download and work with. Essentially from the top to the bottom, what this is doing, it says use a Python 3 image, go ahead, add some users. I'm gonna go ahead and mount a data directory volume onto my Docker image, and then I'm going to go ahead and install the requirements, and then I have this entry point, which basically says spin up a Jupyter notebook. That's my Docker file. Pretty straightforward. So with Docker files, we can easily start controlling when changes happen because you can build a snapshot of what the code, what the data, what all that looked like at a point in time. So I'm a big fan of using the mountable data directories. Essentially what that allows us to do is it takes data on a directory on your local system, and then it's gonna go ahead and mount that into the image. So like I said, we want reproducible results. So if I have one of my data scientists who found a really cool data set and maybe they wanna work on that, but they wanna use the same model, well, they can go ahead and build a new image and maybe rename it with, this is the name of the training data that I had. So in thinking about